Okay, sorry, can everyone see my screen?
Yes.
Okay, perfect. So let me talk about chasing convex functions, and I'll mostly talk about it as almost like a survey, but maybe I'll mention a few details of some algorithms. So let's get right to it. So I'll tell you about this problem. So you're given a point, and at each step, you're given a convex set. So in this case, say dimension is 2, and you're given a point, and your task is to move the point within the convex set. And the cost you pay is the cost you move. And this is what you want to minimize. So once you move in, you're going to be given a new convex set. And once again, you have to move within the new convex set. So again, the algorithm moves, and this time it pays a cost of 2. So we continue this process. And at the end of all the requests, we look at the total movement costs. Okay, so in this case, that the algorithm moved a total of 16. Whereas what we want to compare ourselves to is the optimal algorithm. So this is an algorithm that would know all the requests in hindsight, and it can sort of plan the trajectory optimally. So in this case, it would take this red trajectory, and it only pays a total cost of 11. Okay, so let me make the problem a bit more formal. This is called the convex body chasing problem. Here, you're going to be given convex sets K1 from K2, KT. All of them appear online, so you see one request after the next, and you'll have to make a decision before seeing the next request. The decision you make is the points you place, so how you move your point. And you need to satisfy the condition that the point xi is within convex set ki. And what you want to minimize is the sum of the movement costs. So in this case, I'm going to minimize the L2 norm. And what we want to look at is minimizing the competitive ratio. Okay, so this is the ratio of the cost of the algorithm to the cost of the optimal solution. So let me also just mention that there's a particularly important special case, which is what happens if the convex sets are nested. So maybe this is the picture that you want to keep in mind. So each convex set belongs to the previous one. OK, so the title was Chasing Convex Functions. So why did I talk about convex bodies? And the reason is that we can actually consider the convex function chasing and convex body chasing to be equivalent. So one direction is somewhat easy. We can just set these convex functions to be 0 on the convex set and infinity everywhere. Sorry, one thing I should mention is that the cost now changes. You also pay the hit cost of the convex function. And this sort of reduction was actually given in a paper of Sebastian's. And they showed that these two are essentially equivalent up to a constant factor. So it suffices to just focus on the convex body chasing case. So what I'm going to do is I'll just talk briefly about so there's a lot of history in this problem. So one thing is that this problem was introduced by Linial and Friedman in '92, almost 30 years ago. And in that paper, they immediately gave a square root d lower bound. And there's been a lot of work, especially recently, regarding this problem. And maybe I'll just mention a few key highlights. So one thing is that recently there was a decompetitive algorithm, and I'll just talk about that. So the main sort of result I want to say is that there's this work function Steiner point algorithm, and it achieves a decompetitive algorithm for chasing convex bodies. Okay, since this is only a 10-minute talk, what I'll do is I'll just talk about what the different terms mean, what a work function is, what Steiner point is, and that's about it. So this was, so let me just start with the Steiner point. And this was sort of introduced by Bubeck, Hartak, Lee, and Selke in sort of a seminal paper. And what the Steiner point is, it's an average of the extreme points in all directions. Okay, so what you do is you sample a direction uniformly at random, you look at the extreme point, and then you average all these extreme points. And they gave this really beautiful algorithm. It's sort of a one-line algorithm that says that take the Steiner point, and sorry, given any convex set, take the Steiner point of that convex set and just play that. Okay, and what they proved is that if the convex bodies are nested, then this algorithm is decompetitive. And this is a remarkable algorithm because it doesn't really care about history. It's completely memoryless. And both the algorithm and the proof are sort of like half a page. So it's really a beautiful paper. And once this paper came in, it's sort of influenced all the work that subsequently has come in. And what I want to say is that it's sort of a natural question to ask, can we reduce the general case to this very special case? Okay, and to do that, I'll need to sort of introduce another idea. This was the other part of the title, which is work functions. So work functions are sort of a somewhat natural concept. They say, OK, what's given a point y, what's the minimum cost of satisfying all the requests and ending up at y? Okay. And so here's an example. Maybe you have only one convex set. You're given a point y. If that point is outside the convex set, you'll first need to go into the convex set and then come out. So you have to satisfy the request and then go to y. So in this case, if y is outside, you would pay a total cost of phi. Whereas if you looked at a point z inside the convex set, you would just go directly to the set. Okay. And let me just give you a few more insights. So one thing is that to look at this, we look at the level sets of the work function. So what that means is, supposing somebody told you what opt was, you would say, OK, let me look at all the points where the work function is less than twice the opt. Okay, so this is some sort of an expanded version of opt. So in this situation, let's say k is your set, and omega is your omega would be the set of all points where you can get to that point while at most paying twice the optimal cost. And now I can tell you what this algorithm is. So the algorithm is the following. After you get every step, after you get a new point kt, you compute this set omega t, which is sort of like this expanded version of opt, and then you play the Steiner point of this function. And it turns out that this is d-competitive. I won't really have time to talk about the analysis, but maybe I'll mention that Mark Selke had another way of combining work functions and Steiner points in a very elegant manner. And what he did was he said, instead of taking these work functions and looking at level sets, I'll just define what the Steiner point should be for a convex function. It really doesn't matter what this definition is. I think the main point is that it's a natural generalization. So if you give it indicators of convex sets, this will turn out to be the Steiner point of the original problem. And he also showed, his proof shows that actually the two algorithms are equivalent, but his proof is a little stronger in the sense that he gets d-competitive for all LP norms. Okay, so this is very interesting. But one sort of question that might arise is that, OK, these in modern machine learning, for example, these functions f have very large dimensions. So can we somehow like get better? And Friedman and Lineal showed that you can't do better than square root d. So maybe what we can do is we can maybe ask for better results when the functions have structure. So that's something else we looked at, which is we look at functions that are well conditioned. So if your function is alpha strongly convex and beta smooth, there's something called the condition number, which is the ratio of these two. And the closer this is to 1 tells you how smooth the function is. And in this sort of setting, what we show is that you can get a square root kappa competitive algorithm. And again, in this case, we show that there's a lower bound of kappa to the 1/3. Okay, so there's been a lot of recent work on this. And I'll mention maybe one other strand of work. And this was done by Bubek, Rabbani, and Selke. And what they said was, OK, maybe you're looking at convex function chasing where one point is moved. Thank you. And what they consider is rather, what if you have multiple points? And what they showed is that even with 2 points and 2 dimensions, you can't really hope to do better. But if your functions come from some special classes, like k-means or k-medians, then this becomes tractable. And lastly, maybe I'll just mention that there are lots of still open questions in the area, but sort of the main ones are, can we close this gap for general chasing, which is, can we do better than O of D in the upper bound? At least that's what most people believe is the correct answer. And similarly, if you're well conditioned, maybe we can do better than this square root kappa and get closer to this kappa to the 1/3. So lastly, I'll just briefly mention that I work at Google Research Mountain View. Google Research is enormous. There's lots of different participants. But even in Mountain View, we have a strong theory presence. And we sort of focus on all kinds of things. I'll just mention 3 things: algorithmic game theory, online algorithms, and discrete algorithms. And there's many of us on the call. So if you're interested, we'd love to talk to you. Thanks.